This week we are going to dissect nematodes. Nematodes are a branch of worms. There are terrestrial, freshwater, marine, and parasitic forms. We call nematodes roundworms. There are also flatworms like planaria, and then there are like kind of the true worms, the earthworms that we call annelids. This particular species is called Ascaris, and it is a parasitic intestinal roundworm. So this is something that can actually infect humans and kind of reproduce inside your intestines. One of the features demonstrated by Ascaris and by many other species is one called body size sexual dimorphism. That's when we notice a difference in the overall body size of males and females. Now, we've talked about this in class, and we talked about how for at least mammals, males are typically larger than females, but for many insects and for these parasitic worms, it's actually females that are larger. So here on Ava's tray, we see two specimens. If you'll straighten them out, Ava. One of these specimens, the smaller one, is very likely to be male. We'll confirm that when we get inside. And the other one, the longer one, is very likely to be female. So one way, please be quiet guys, one way to tell whether your specimen is male or female is that males have two what are called chitinous spicules down near their anus. And so this is what allows the sperm to actually ejaculate. I'm going to try to see. I don't know that we can actually focus on this. Yeah, we're not going to really be able to focus on it. This is something that you need a magnifying glass to be able to see. But this specimen, actually the longer specimen on Ava's tray, has those two chitinous spicules at the end. The other end is the head end. Move this one out of the way. And on the head end, if you can look very closely, you can see how there's a top lip that kind of overhangs the bottom lip. So it's kind of hard to see. Again, it's a little easier with magnifying glass, but you can see how the top lip kind of protrudes over the lower lip. All right, so the next step in dissecting these roundworms is to orient the body of the worm so that the dorsal or the backside is up, the ventral or the belly side is down. The skin has a thinner wall on the dorsal side. So we used the mouth parts and the lips to be able to orient this specimen, ventral to dorsal. And now what we're doing is we're very gently cutting through the ventral skin to use then the pins to separate the skin from the rest of the internal anatomy. All right, so we've opened up two specimens here. One of them is male and one of them is female. So we're going to kind of point out some specific features. These take a lot of pins to hold them apart. First of all, for both of them, we started at the head. So we didn't actually cut all the way up to the female's mouth. We did for the male. So we'll look here. You can see really from the head on down, you've got one consistent kind of passageway, and that is our up at the mouth, the pharynx, and then our digestive tube that goes all the way down. Sorry, I can't find my pointer. All the way down to the anus here at the very bottom. Okay, so that's one thing that can clue us into whether we have a male or a female. Both of them have this kind of I have a hard time with depth perception, guys. Both of them have this kind of thin, kind of fibrous stuff. In the male, these are the testes and the vas deferens. The testes, of course, being the site where the sperm are produced. The vas deferens being the tubules that then travel all the way down to the seminal vesicles and then the ejaculatory ducts. When we compare that then to the female, in the female, we've got our digestive tube down here, but we also have two very distinct passages here that are actually, each of these represent a uterus. So we've got multiple uteri. We've got two uteri, two long uteri in these females, and we've again got all of these tubules that kind of surround the uteri. These are the oviducts, and if we were able to separate them out, which we can't just because it's really hard to do, and these things come apart at the slightest texture, we would be able to trace them to the actual ovaries that would be at the end point of those oviducts. So we see a difference between these two, not only in size, but also in their internal anatomy. So for these roundworms, really essentially, we were able to view two systems, right? We don't have a heart. These are not organisms that have fully closed discrete circulatory systems. We do have an excretory system that comes at the end of the digestive system, so going here on this male specimen from the mouth through the pharynx, through basically the intestine, all the way down to the anal opening. On the female, again, coming from the mouth, through the pharynx or the throat, through the intestine, all the way down to the anal opening. So we've got a digestive / excretory system, and we're able to see these differences in the reproductive system. For the female, most of what's called the pseudocele, this basically from throat to anus, kind of abdominal cavity, most of that in females is taken up by the uterus and ovaries and oviducts. One of the reasons that this is the case is because these are parasitic worms. So when we think about what parasites are kind of built or evolved to do, they're evolved to reproduce at pretty high rates to continue or kind of provide this continuous infection. So these females are very clearly evolved to reproduce. Their uteri can hold up to 27 million eggs at a time, and females are able to lay more than 200,000 eggs per day. For the male, we saw also the reproductive system. This single long tube made up of thread-like testes as a thicker vas deferens. Both the males and females are coiled. And the distinction with the males, of course, is that they have these ejaculatory ducts down near the anus. There is no respiratory system. There is no circulatory system. These organisms live in moist environments where they're absorbing air essentially through water through their skin, and where, because their body is constantly flushed with fluids, the movement of the fluid itself is what takes the oxygen to the various regions inside the body.